There is some problem with my camera. Is it okay if I go without the camera on?
Yeah, it's okay.
Shranti, can I start?
Yeah.
Okay. So, hello everyone. Today we are really excited to have Professor Monojit Choudhury with us. Professor Monojit Choudhury is a professor of natural language processing at Mohammed bin Zayed University of AI at Abu Dhabi. Prior to this, he was a principal scientist at Microsoft Research India and Microsoft Theory. Professor Choudhury's research interests lie in the intersection of NLP, social and cultural aspects of technology use, and ethics. In particular, he has been working on multilingual and multicultural aspects of LLMs, their use in low resource languages, and making LLMs more inclusive and safer. He also uses AI to explore the interaction between language usage patterns and sociocultural norms and values. Professor Choudhury is the associate editor of the communications of the ACM and IEEE transactions on pattern analysis and machine intelligence. He has 150 plus publications in peer-reviewed journals and conferences and has won several best outstanding paper awards in ASL conferences. Professor Choudhury takes a keen interest in popularizing linguistics and AI through puzzle solving. He is a general chair of Indian National Linguistics Olympiad, the founding co-chair of Asia Pacific Linguistics Olympiad, and the founding board member of International AI Olympiad. He holds a BTech and PhD degree in computer science and engineering from IIT Kharagpur. So we are very excited to have you today. Over to you, Professor Choudhury.
Thank
Hello.
you.
Good afternoon, sir.
Good afternoon.
So we have shared your screen and just the class will take about 2 minutes to settle down. Can we begin after that, please?
Sure. Just let me know when to start. Thank you.
Definitely, sir.
And could you also let me know how long I should keep the lecture?
Yes, sir. We have the lecture till 5 p.m.
5 p.m. meaning
It's a 1.5 lecture.
1.5 hours. Okay. So I'll keep it to around 1 hour,
Yes,
close to it, and depends on if people
Professor,
have
what do you
questions.
think everyone in the class? Is it clear? The audio in the- Just give us 2 minutes, sir. We will fix the audio in the class.
Monojit,
Yeah.
could I ask you to go a bit slow, please? There are many new students.
Sure.
So take 1 hour, 20 minutes, no problem. Any time up to 1.5 hours.
Sure. Yeah. No, I was thinking like the content could be 1 hour, and then in between I'm expecting questions, or maybe after the talk there can be questions. So with questions it will stretch to 1.5 hours maybe.
Hello, Monojit.
Yes.
People don't ask too many questions. So please go ahead. Yeah.
I see. Okay. We'll see. Let me know when to begin. I'll start.
Kiran, is the class settled?
Kiran, can we begin?
Kiran nudges. Can we start the class?
Yes. Yes, we can start.
Yes, sir. You can start the class.
Sorry? Okay. Okay.
Yeah.
Good afternoon, everybody. First of all, thanks for the invitation to do this guest lecture. I would have definitely loved to do this in person because that I feel is the best way of interacting with all of you. But unfortunately, I couldn't be there, so I will do it. I had to do it online. But anytime you have any questions during the lecture, please maybe raise your hand on Zoom or in the classroom, and I'll just request somebody to moderate. I'm more than happy to take questions during the talk. But of course, after the end of the talk, there will be also time for questions. So please don't hold yourself back if you have questions. Yeah. And as in the beginning it was mentioned, so I'm professor at Mohammed bin Zayed University of Artificial Intelligence, the first AI university in the world. It is in UAE, Abu Dhabi. And also one interesting fact, today Sam Altman was here. I mean, usually a lot of things happen in the university, but this was something, a special moment for all of us, and it just happened today morning. So I thought I will share with you. So the university conferred an honorary doctorate on Sam, and he was there and he was interacting with the students and all that. So pretty exciting, a lot of things happening. Anyway, so the talk that I'm going to give is more based on the research that I'm doing at the moment. And the title will be clear as we go along the talk, why I call it Turing Test 2.0, and what does it mean, and why this is important, and so on and so forth. Okay, so without further ado, let's jump into the topic. So the whole notion of trying to build something like a ChatGPT, actually, if you think of it, comes all the way back from Turing, right? So Alan Turing in 1950 wrote this famous paper. I think the title of the paper was something around "Can Machines Think?" And there, this quote appears where he says, "It is not difficult to devise a paper machine." By paper machine, he means a program or a code, which will play a not very bad game of chess. In other words, what he's saying is it is imaginable that programs can be written to play good chess. Are there imaginable digital computers which would do well in the imitation game? Now, Turing defined what an imitation game is. imitation game is what we call today the Turing test. And many of you might immediately recognize also there is a movie named Imitation Game, which is a biopic on Alan Turing. If you haven't watched it, I would highly recommend watching it. I mean, of course, it's a movie, so it's not everything shown in the movie is true. It's historically true, but it's nevertheless a very good introduction to Turing and his life. Now, what is an imitation game or a Turing test? As you would all know, I'll just repeat because some of you may not know it exactly the way Turing phrased it. So there are judges, human judges, and they are chatting with something on the other side of a wall. And what is there they don't know. And based on the chat, they have to say whether it's a human or a machine. And if they believe the machine to be human, most of the judges get fooled by the machine that it's a human, then that machine has passed the Turing test. And this became the holy grail of AI all through. And that's why NLP, because it's about chatting, chatting is language, and therefore natural language processing became the cornerstone of everything that AI could, of AI. And in fact, many people said NLP or language understanding is a AI complete problem. By AI complete, they mean all problems of AI could be mapped to this problem. So this problem is as hard as any other problem in AI. And if you solve it, you solve all problems. Now, there are two interesting things to note here. First, is Turing was quite prescient because he predicted that chess will be very not so difficult, but imitation game will be very difficult. And as you might recall, in 1990s, we already had Deep Blue from IBM, which beat the grandmaster, I think it was Kasparov at that time, on chess. Whereas until 2020, there was no sign of any, AI system which passed the Turing test. By the way, there is a prize. I don't know if you have heard about it. It's called the Loebner Prize. It was instituted in 1990, and it would be given to the best chatbot, which would pass the Turing test. And of course, none of the chatbots in those days could pass Turing test. But the second prize was given to the chatbot, which came close, right? Which were best among the submission. And I think around 2013 or so, I forgot the exact year, there was a chatbot which passed Turing test. And how it passed was they were very, how do I put it? They were very smart, the people who designed the chatbot. It wasn't that the chatbot was very smart, but the people designed it in such a way that the chatbot claimed to be a person who is a 13-year-old Ukrainian boy who knew little English. And the test was, the imitation game was played in English. Now, when people were talking to the chatbot made mistakes in English, and it sometimes said random things, but people thought it's a Ukrainian boy, his native language is not English, and 13-year-old, so maybe a crazy teenager, and maybe that person can say these kind of things. And they tried to make sense of whatever garbage the chatbot was yielding and thought maybe it is a human. And it was one of the first cases of a system winning Loebner Prize. And of course, this also shows the limitation of Turing test, right? The limitation of Turing test is, there are gaps here. So that's one point, that Turing was quite prescient that chatting or conversation agents are much harder to build. And I'm not getting into why. I'm sure you have a sense already of why chess is easier than natural language processing, right? It took much longer. Practically, I would say Turing test got solved only in 2022 with ChatGPT coming in. Although I will also argue that not in a full sense, in a limited sense, it got solved. But there's evidence for it also. In 2020, they discontinued Loebner Prize, saying that it's no longer useful. Sort of Turing test is no longer an interesting thing. AI can pass it very easily. So that's one point. The second point I wanted to mention is, and here the SAM's reference earlier he was talking is relevant. So OpenAI started back in, I think, 2016 or 17. And at that time, when they went to Microsoft for funding, they showed a demo of a robotic arm grabbing a coffee cup and showed that, okay, they really can build strong AI system and therefore ask for funding. And I think most of Microsoft board almost agreed, except for Bill Gates. So Bill Gates said, no, that's not a good test of AI. I would believe in OpenAI, or for that matter, any company, if they can build a system which can read all the material that's there on the web and make sense of it and reason over it. And that's when OpenAI tried pushing in the direction of LLMs, which would later be called LLMs. So they first built GPT-1, which was a very, very weak system. By today's standard, it is a very weak system. Then GPT-2, which is also not a super strong system by today's standard. But at that time, GPT-2 did make a little bit of noise, although the actual noise was made when GPT-3 came. And they went back, I think it was 2018 or so, again to Microsoft, or 2019, I forgot the exact date. I think 2019, because GPT-3 came in 2020, right? So in 2019, they again went to Microsoft showing GPT-2 and asked for money. And that time, everybody was convinced that something bigger was going to happen. So in some sense, Turing's code sort of is the reason for, I think, Bill Gates' quote or the statement, and which is sort of the cause of all the ChatGPT and AGI and all the revolution we are talking about, right? So yes, this is a very important, like, defining moment in the history of AI and mankind. Now, what I'm going to claim here is Turing test 1.0, which is what Turing had originally said in 1950, is effectively this, right? Can computers imitate a person, imitate any non-specific person, right? So that's why you could claim a 13-year-old Ukrainian boy, or you could claim a PhD holder in AI, and whatever you claim doesn't matter, as long as you can make believe that it's a human. So it's like imitating any non-specific human. And that's the loophole of Turing test. And using that loophole, you can easily also pass Turing test. Easily is a relative word, by the way. It was not so easy until ChatGPT came, right? So you should take it in that context. So I would say Turing test 1.0 is solved. Now the question that I am asking is, can we solve Turing test 2.0? Which is, can computers imitate a specific human? For instance, I could say, can a computer imitate me, and talk to you in a way. So I don't go to a meeting, I send the chatbot, and let's say it's an online meeting, and it does the meeting and comes back, and nobody even realizes that I wasn't in the meeting, right? So can a computer imitate a specific human? And it could be anybody. It's not me. I mean, that the specific human is a variable that's an input to the model. And it could be Professor Pushpak Bhattacharya, or it could be Monojit Choudhury, or it could be any of you. So can we do that? So what I'm going to talk about is some research projects around that direction. And of course, as many of you would be already thinking, oh, is it even a good thing to do? Why would we want to do that? Isn't it ethically problematic? So we'll also get into those questions. So that will be the broad theme or agenda for the talk. So first part of the talk, what I'm going to argue is why this makes sense from a scientific point of view, not the ethical point of view or practical point of view. Those will come later. But from a scientific point of view, from a problem formulation point of view, why this makes sense. So here is the argument. So what are LLMs, if you think of them? LLMs are trained on data like this. So this is like text. Now, where does this text come from? So its job is to predict text, right? So where does this text come from? This text is generated typically by human. Either humans wrote it, or humans spoke it, or humans typed it. Of course, you can also argue there is synthetic data and all, but that's like now. But when originally all these things were trained, or at least we expect these models to be trained on human data, human generated data, and be able to predict what's coming next, right? And why only text data? We all know that, yeah, so you can train these models on any kind of sequence data, right? So text is one example. You could do it on images. Of course, you can do it on speech signals. In general, imagine these are different emotional states that are there a person is going through, and not one person, single person, many people and their emotional states. Then if you train an LLM, it should be able to predict people's emotional state and how they go through it, right? It's just a sequence predictor. It could be stock market prices or anything, but I'm mainly focusing on human behavior. Stock market prediction is a more complex thing. It's a collection of human behaviors, right? Many other things goes on. But if you think of emotional state, language, it's typically generated by one human at a time, and LLMs can model that and predict that. Then, if this is the thing, then from a machine learning point of view, what should be the test for generalization, right? We always, in machine learning, when we build a model, we always ask this question of generalization. And how do we test it? We always do test, train, divide. So here is my training data on which I'm training the model. And I don't test it on the same data, right? We have a separate hidden data set on which we test it. And if its performance is good on the held out or separate data set, the test set, then I say the model has generalized well. Otherwise, the model is overfitting to the training data. So what I'm arguing is, since it is being trained on human behavior, language is a human behavior, speech is a human behavior, it could be anything. The test also should be about predicting human behavior, but the test train split should be that one comes from one set of humans, the other comes from another set of humans. Because if it comes from the same set of humans, then you run into the issue of contamination. And this is what we are seeing. We tend to see, because we don't separate it by humans who are generating the data, right? We mix it all and then separate it by some random split. And therefore, I mean, there is a lot of this question, right? Whatever it is generating, is it a memorization or is it an actual understanding and generation? And many people claim it's a memorization because almost everything was in the data. And I'm saying, my point is that yes, it's possible. And if you really truly want to test it, try to test it on held out humans whose behavior the model has never seen, and now try to predict on them from some context. And we'll come to what those contexts might be. Of course, if I have never seen a person, don't know anything about that person, I cannot predict anything also about their behavior. But if I see certain behavior, a little behavior, can I generalize and predict better on more behavior? Like, can I keep completing the sequence? Now, let me try to contextualize this whole notion on what we are doing today, right? On exactly how, because people are not looking at the problem in this way, the way I'm saying. So people are looking at it in different way, and I'm now trying to connect. So how people are looking at it, so there are two schools of thought. One school, and this is the most popular school, is, we try to evaluate LLMs on different kinds of tasks. So this paper, which is one of the best paper award receiver from, I think, NACL, was it NACL or ACL? I forgot, 2025. I mean, this year itself, was about these various kinds of, data sets, like instruction following data sets, refinement data set, multilingual data set, reasoning, and so on. This is what I would call what behavior is being predicted, not whose behavior. Note that I'm talking of whose behavior. This is what behavior. Now, what behavior, of course, this is very important. It's talk about capabilities of agents. But the argument is this may not be the best test of generalization, because this is still like, you might have seen this kind of behavior a lot in the data already. So this is like what kind of capabilities a model has. But we are asking a different question, which is whose behavior is being predicted. Now, there are there are multiple levels of defining whose behavior. If you just ask for universal behavior prediction, all these data sets that I talked about, many of them actually are about universal or what I call normative behavior prediction. For instance, what is the capital of India? That might be a question in MMLU, right? This is a pretty common question in many of these data sets, this kind of question. Or I might ask it a reasoning question. Somebody had 5 apples, gave 3 apples to their friend. Now how many apples they are left with? It's a mathematics problem. Typically GSM 8K data set will have this kind of thing. And what answer do you expect? For the first one, New Delhi. For the second one, 2 apples. Now, why? Because this is the normative behavior. If somebody were to behave normally, you would expect that. But if you think of actual humans, they may not follow the normative behavior, right? There is a lot of variation. For instance, somebody might say, I don't know the capital of India. I'm not from India. I have never heard about the capital of India. That's a very valid human behavior. Or somebody might say, 3 apples, you have given somebody 2 apples, 5 apples, 3 apples, only 1 is left. And maybe that shows somebody hasn't learned math yet or is doing mistakes, silly mistakes, whatever, right? So this is a very natural human behavior. If you are talking of Turing test, right, where you have to imitate humans, then these have to be captured. Now, you might imagine that, these are like, why would even we want to capture mistakes? And I will tell you why mistakes are very important. So these are not always about mistakes. These might be also about how people in different parts of the world think differently, right? So we talk a lot these days about culture-specific benchmarks. So for instance, if you ask to resolve ethical dilemmas, or if you ask, what is your favorite food? The answer might vary if you are asking people from India versus if you ask people from Africa versus US and so on and so forth, right? So unlike the factual questions and the reasoning questions, there are actually real questions where it matters whose behavior are you modeling. So it's not just a case I'm making out of the blue. There is a reason that this is important. And indeed, there are a lot of these culture-specific benchmarks which try to model this kind of behavioral differences by people coming from different countries, different religion, and so on. However, I would argue that these data sets model what we call stereotypes. For instance, if the question is what kind of food is your favorite, we can't just assume a person from India will say biryani or dosa. Yes, biryani and dosa are common in India, but a person might still say pizza or sushi, right? I'm sure there are many Indians who might say pizza is their favorite food or sushi, but these are not typical Indian food. So whenever we are talking of culture in an average group behavior kind of thing, instead of averaging over all the humans, I'm averaging now over a smaller region of humans, but still it is a stereotypical behavior, right? So we don't want to, we are not capturing the variation within that group. So the question is then, can we move to one person and predict their behavior? Now, this is exactly coming back to Turing test 2.0. And of course, there is a particular version of this kind of tasks which we are all familiar with, which is personalization. For instance, recommendation systems, or even these days, people talk of digital twin, sort of the example I gave. And I would say these 3 things are a continuum. For you, from universal normative behavior to group average to personalization, they are not separate tasks. They are a continuum. And this is what I'm going to show in the talk, like through some experiments and some modeling. This is a continuum, and why this whole modeling, this whole continuum matters, right? But there are people who are interested in languages because it's an NLP course. So let me also mention that there's the equivalent of this in linguistics. So language, like English is a language, but English has varieties. So sometimes we call them dialects, sometimes we call them varieties. So American English, Australian English, Indian English, and so on. And then even if you look at one particular person's English, it will be different, right? Even 2 Indians speaking English would talk differently. And there is a term for it. It is called idiolect. So idiolect is like individual's dialect, sort of. So there is a correlate of this in linguistics also, which I wanted to mention. So now what I'm going to do in the rest of the talk, with this, I hope I'm able to make a case that, okay, it makes sense to study personalization as a lens to look at LLM generalization capability. We are already doing it, but not to the extreme. We are kind of stopping at the culture level or the group level. And personalization is something people are talking about these days, but they don't connect the whole spectrum. And I'm saying we should look at it as a whole spectrum. So I hope you are with me and sort of agree. Now, if that is the case, what we are going to do next is I'm going to talk about two example case studies. One, which is like taking traditional recommendation system kind of task and show to what extent we can personalize. There will be some benchmarking with LLMs and all, but that is secondary. I would ask you to pay attention to the modeling part, which I think is more interesting. And second is a more practical example of this, how we can use it to do some real work. I mean, to bring some utility to people. That's a system called Culturally Yours that I will describe. And finally, I will end up with a whole bunch of ethical and philosophical questions of what might be a problem of this kind of a pipeline. Okay. Okay. And before I get into it, let me just quickly acknowledge the people who are involved in this work, and Shogoto Shah, a postdoc in my group, and Saurav Kumar Pandey, who was earlier a research associate, has been the primary contributors of the work that I'm talking about, and also my colleague, Alham Aji Fikri. And it was supported by Microsoft Research Azure Foundation Model Research Grant. Okay, so let me begin by giving a very brief primer to the culture side of things, because like we said, culture is about group behavior. So let's start from there. Recently, there has been a lot of interest in culture. People have been talking about why modeling culture is so important for LLMs. And frankly, I also got into this whole direction of research coming from culture. So we did a survey last year, and we found, first of all, that the number of papers in this area is growing, right? Each quarter, how many publications are coming, and it's skyrocketing, actually. This year's NACL was also themed on culture. And most of this work broadly come up with one conclusion, that LLMs are biased towards Western culture, and most of the non-Western cultures are underrepresented, and so on. So that's a common theme. But like I said, this generic conclusion doesn't make much sense because no culture is a monolithic group. For instance, think of, like we usually talk of India or, Italy as cultural units, right? Nations as cultural units, but culture can be about anything. So imagine all scientists in the world, right? They define a set, and you can talk about their culture. Of course, it will be very varied, but there might be other kinds of behaviors that might be more common across scientists. For instance, scientists might be more inclined towards reading books than an average person, right? So there are behaviors which are more common to this set than the average of the whole set of people in the world. So in general, we can say behavior is a distribution over a set of options, right? Cultural behavior is a distribution over a set of options. And now if you take all scientists, that will give you one kind of distribution. But then when we make this group smaller and smaller and more particular, so I can then talk of computer scientists. And now I ask the question, are computer scientists any special compared to all scientists? Do the behavior change when you bring it from all scientists, the distribution of all scientists, to all computer scientists? And the answer would be yes. I can totally imagine, again, food, what they like to eat, that may not change. That might still remain pretty random distribution, right? But for instance, what conferences they typically publish in will drastically become more peaky, right? If you see all scientists and what conferences they publish in, it will be a wide distribution. Computer scientists, it is much peakier distribution, right? Or even if I ask, so for instance, if I talk of all NLP scientists, who is a subset of it. So if I ask, conferences, it will get even more picky, but I will tell you even more interesting cultural fact about NLP scientists. So if you ask this question, do they write the related work as the second section or the second last section? So NLP scientists will typically write the related work as the second section of a paper. That's the culture, right? Whereas in other work, like let's say systems, the systems papers, you would see that typically the second last section is the related work. So these are cultures that have evolved, right, in these scientific communities. But note that these are what I would call undocumented cultures. I mean, I'm telling it because I know, but you won't find a documentation of that culture. On the other hand, when people talk of cultures, they talk typically of documented culture. So Indian culture is a documented culture. There are lots and lots of books written on that, right? And so is for, let's say, culture in corporate world versus non-corporate. So corporate culture is a term, right? So there are certain cultures which people study and have documented. But it is important to remember that culture defined as a behavior of a group can be also undocumented. That doesn't mean you can't call it a culture. So you can't, is NLP scientist a reasonable unit to study culture? Of course, yes. As long as they show idiosyncratic behavior, which is different from the bigger set. So this is the point I'm trying to make. However, then there is a complication. Now imagine IIT Bombay, all the people in IIT Bombay, right? They also define a culture. I'm sure there are certain lingos and slang terms only used in IIT Bombay. All different IITs would have lingos, which are different, but also there are similarities and so on. Now, what about this intersection? NLP scientists from IIT Bombay. Now, this will be a very interesting intersection, right? They will have some characteristics of IIT Bombay, and they will have some characteristic of NLP scientists. And this also defines a culture. So in this way, when we operate as humans, our behavior is controlled by multiple hats that we wear. And this is a known fact. Whatever I'm saying is nothing that by the way, all these things are something which social scientists and anthropologists who study culture have already said. I'm just merely trying to explain this to you. So we wear multiple hats. For instance, sometimes some of my behavior can be explained by the fact that I'm from India. Some of my behavior can be explained by the fact that I'm a computer scientist. Some of my behavior can be explained by the fact that I'm a man, or maybe I'm in the age group 40 to 50. And these are all different hats that I wear. And a random combination of those can be the causal, can cause certain behavior. So in other words, the space is extremely, extremely complex, right? It is an extremely complex space, and it's a long tail. By long tail, I mean now this intersection can go on and on and on. Where do you stop, right? So the only logical point of stopping this intersection is person, an individual. But individual also can wear multiple hats. And this is the point why I'm saying this is a continuum, that what group you are looking at, the behavior distribution changes from there. And then why culture is important, why knowing the distribution of NLP scientists' behavior might be useful to predict my behavior. Because I'm an NLP scientist and this distribution gives you a good prior, even though I won't do everything which an NLP scientist do, right? I will have my idiosyncrasies, but that provides a good prior. Let me give you another example. If I'm talking to an Indian, just by the virtue of the fact that I know that this person is Indian, I can immediately, assume that they know who is Narendra Modi. They know where is New Delhi. They know, what is biryani or what is a dosa. I won't make this assumption if I'm talking to somebody from Philippines, right? They might know these things, but I won't make these assumptions. So this is what I mean by cultural knowledge provides a prior. Now, why this prior is important? This prior is important because this helps you to communicate. For instance, when I'm giving this talk, I'm not explaining you what is an LLM. And this is simply because, I know that you are doing NLP course. You all know what an LLM is, right? I might not tell you a lot of other things. I'm just assuming because I know that you have that background. So similarly, knowing somebody from a particular cultural group helps. But as soon as I start talking to somebody, so suppose you know biryani and dosa, and I might assume that you might like biryani and dosa or dosa. But then eventually you tell me that no, I am actually more a pizza fan. So as I know you more and more, think of your friends, you know them so well that now the priors don't matter. So once you have personalized and build a model of your friends, the priors become irrelevant. So yes, priors are stereotypes and biases. They get us going with a conversation. But as soon as we know a person better, we don't need the priors anymore. So that is the whole point of why we should start from culture and normative behavior. But eventually the goal of a model should be to understand a person and be able to predict an individual's behavior. Okay, so this is the theoretical part of the model. Now let's get into the mathematical part a little bit. All these things that I said, what it would mean mathematically. So mathematically, consider any particular behavior. For the sake of ease, let's say what movies people like. So take the universe of all people and ask their movie choices and draw a curve, right? A probability distribution, sort of which movies, how many people like. You will get a wide-ranging distribution. So let's call that distribution PB. B stands for behavior. And if I compute the entropy of that distribution, I hope you all know entropy. Again, I might be wrong here, but I'm just assuming you all know entropy. And it will have some value. Now imagine I break this set by countries, India, USA, Mexico, etc. And then I take a particular country, let's say India, and now I do this distribution, probability of a behavior given a country, and calculate its entropy. What do you think? Which entropy is going to be higher, right? So in general, if this is a valid dimension of culture, across which the behavior can be predicted better, then this is the relation you expect. The entropy of behavior of all users would be much higher than entropy of the same behavior from a particular country. Of course, given that that particular behavior is modulated by that particular cultural dimension. So in case of movies, I think country is a good predictor of behavior, right? And then you can further go and divide it by, let's say, other dimensions, let's say gender. So India, and now you take another subgroup, Indian male, and now you calculate the entropy. And you might be surprised to know in case of movies, there is a distinction between what men typically like, the distributional differences between what men typically like than female typically like. So the entropy will further reduce. And it will keep going down, down, down as you come to smaller and smaller reasonable groups, right? So this is the trend we know happens in the world. Now, the question is, do LLMs understand this? This technically is called metacultural competence. This whole point of knowing this fact that as we go to smaller groups, the behavioral distribution becomes more and more peaky. Psychologists call this metacultural awareness or metacultural competence. And knowing about a particular culture, like what is the capital of India, what are common foods in India, is called cultural awareness. These are two very distinct things. Somebody can be metaculturally aware without knowing a particular culture, right? So for instance, I don't know which movies Indian males typically like. Frankly, I don't know the answer. But I know that this set of movies is going to be more specific than this set of movies, right? So that the direction of entropy I know. So this is what is metacultural competence. And by the way, this is an innate thing which apparently all humans have, and that helps us to navigate. And ideally, we want to see if LLMs have that. So let's do some experiment to see if LLMs have that. So the experimental setup is as follows. I start with, so unfortunately, getting data sets for this kind of experiments is very hard, right? Because we are talking of all these variables like country, gender, etc., whatever variable matters, and also people's preferences or behavior, right? So where do you get this data? It's very hard. Fortunately, I mean, in recommendation systems literature, people have done some research here. So there are two data sets that we could get. One is called Movie Lens, which is about people's movie preferences, and one is Last FM, which is about song. And these have not only preferences, but also things like which country the person is, what age group, and so on and so forth. So we did have a few different variables. So it's not a very comprehensive data set, but at least we could begin our study with it, right? And this is the expectation that if I don't specify anything and say which movies are typically favorite and look at the entropy that of the LLM's responses, versus if I give like a user from India and look at the entropy, user from India, age 20 to 30, loves these movies. Already I know loves these movies. This is even a smaller set, right? So I can try these various combinations and see what I get. Now I will define three quantities. The first is the true entropy of the data set. So I have this ground truth data set, right? Let's say Movie Lens, I have it. So by formulating these queries, I can look at the exact distribution, at least in this data set. And from there, I can measure the entropy. Let us call it the target entropy or the ground truth entropy. I can also calculate the model's prediction for the same situations and calculate, and model's prediction will be also varied, right? As you can imagine. It's not like one or two movies that the model will predict. The more details of exact experimental setup and all I can get into if you are interested later, or you can read the paper. And then that's what we call H model. And then we can calculate the cross entropy between these two distributions, right? This is like H cross. We will call it H cross. Now, this cross entropy, as you would know, has to be always greater than the target entropy, right? The minimum value of the cross entropy, what the model predicts, cannot be lower than this. So if we predict the target entropy in this axis and cross entropy in this axis, this is the ideal line that the cross entropy should take, x equals y line. That means the model is predicting the exact behavior that I expect. But what would we expect? So model will never be able to come on this side, right? So cross entropy has to be always higher than target entropy. So it can be only on this side. So what I'm claiming is initially when this set is very large, like all Indians or the whole set, the target entropy is large. And I think model will make reasonable prediction. Why? Because model has been trained on data from a lot of users. So initially, when this entropy is large, target entropy is large, cross entropy will be nearly close to target entropy. But as we go down, it will start diverging. So essentially, model will start losing depth of prediction. It don't know how that small group uniquely behaves. And as we come to the very end of the spectrum, now here we are talking of individuals, and model will start failing miserably, right? It should not come here. The other prediction, so by the way, this point is what we call the point of inversion. Like after this, the generalization stops. Up to this, there is still some sign of generalization. So this is called the generalization zone for the behavior. And imagine there are two models, a purple model and a green model, and you get these two curves. Then the question is which model is better? And as you would have by now figured out, the purple model is better because the purple model has a far, its inversion point is far towards the left. So it has generalized more. Now, we want to see if these things happen when we do the experiment with the last FM dataset and the songs dataset. So what we do, I will explain these graphs one by one. So first, let's see the models we try. For all these graphs, the models are same: GPT-4o, GPT-4o mini, llama. And then the red line here means random. Random meaning we don't use any model. It's just a random prediction of movies or random prediction of songs. The top ones are for movie, bottom ones are for song. So let's first see the movie thing. See, the curve is similar to what we expected. So, of course, it's not close to x equals y. It is quite above that, which means it's ability to predict the distribution is much poorer than what we drew or we expected in the previous graphs. However, the trend is same. So there is an inversion point here. It generalizes to certain end and then starts deviating. So it's almost magically like this, right? And by the way, this was an aha moment for us because we drew these graphs on my board in my office in the board. We drew this graph and then went and did the experiment. And then when you get to see this, it's like, aha, this is exactly what is happening as we are predicting. And the other prediction that you can draw from here is random is the worst because further it is from x equal y, the worst it is, right? Then it is llama, and GPT-4o and GPT-4o mini was quite similar for these tasks. And there's a clear gap between random and llama and this GPT-4o model. This is also something you expect. So in some sense, what we are predicting or expecting is happening. Now, what are these three different graphs? Very quickly, this graph is when we have both proxy. I didn't define what a proxy is. Proxy stands for demographic proxy. So what is the country? What is the age group? What is the gender? These are called proxies. And history is for a set of users who liked already these movies, right? So that we call history, like the behavioral history that we already know. So when you give both proxies and histories, this is the behavior. This is the curves that we see. When you give only history and no proxy, we see similar, like it starts kind of with a similar trend, but the inversion point is quicker. And when we start with only proxies, we do see a much better, sort of line. But of course, these graphs are not exactly comparable because the data sets are different, right? You are breaking the data set in different ways when you are doing this experiment, like the subgroups that emerge are different. But nevertheless, like here we see the inversion point somewhere at this place. And random has absolutely no generalization, which is what one would expect and so on. Songs show a different behavior though. The generalization zone is very small, very small. And when you give no history, it can't generalize at all. Nothing actually generalizes. GPT-4o, very little, very, very little, just a small zone here. And why this is so? It seems like it's much harder to predict somebody's choice of songs based on which country they are from or only like little bit of information. Whereas movies, it is far more easier. So like I said, it also depends on...
Dramatics would like to participate in upcoming MD.
Sorry, if you are, not talking, please mute your phone. Yeah. Okay, so what's happening here is clearly movies are more predictable with these proxies, which songs are not. But songs can be more predicted from the history. This is what it is saying. So we will now switch gears. One interesting question we'll come back to later about this study is there an inherent limitation? First of all, two things. One is there is a huge scope for improvement here. As we can see, LLMs are not yet there. So all this AGI story and everything, if you look at it in the Turing test 2.0 frame, there's a lot to be done here, right? And the second thing I want to say is, it's a very interesting philosophical question to think about that to what extent a person's behavior can be predicted, because there should be an inversion point for sure, right? And how do we know we have reached that inversion point? So is this the actual inversion point? Maybe after that, it is impossible to predict whether a person, even you don't know which movies you will like after a point, right? We also don't know our own behavior to the very extreme. So it's an interesting question. Okay, let's switch gears here and go to the second case study that I wanted to tell you. This is about culturally yours. So it's a cross-cultural communication assistant that we are building. What it does is it's like a browser plugin. You download it and install it on your browser. Then it will ask you a few things, like which country you are from, where did you do your studies, and are you from a city or a village? Few such questions, 3, 4, and then it will, whatever you are reading, based on what you feed in the information, it will try to predict what you might not understand. So for instance, suppose there was this statement, there was this thing that you are reading, the elaborate description of the food items makes me want to drive to the nearest golden arches. Now, if you are an Indian woman of certain age, it might think, the model might come back saying, oh, Vana is something you won't understand. Golden arches is something you won't understand. And then if you hover the mouse over this, it will explain. So in ways that you will understand. So it might say Vana is a way of writing 1, 2. Or golden arches refers to the McDonald's fast food chain. And similarly for other countries, other age group, etc., it will give something different. Now, the point is that this is the starting thing. Culture is a prior. You might actually know what is Vana, but not know what is golden arches. So you might say, give feedback to the model that, hey, I know Vana, so remove this from suggestion, but keep golden arches. Based on that, it will keep personalizing. So more you use the model, the more it will understand your, what you don't know, what you find hard to understand, and accordingly, your suggestions will be more customized. So this is the idea of the tool. And as you can imagine, behind the scene is an LLM agent. And again, I'm skipping the details of how we build the LLM agent, because that's an active area of research. The initial LLM agent was built in a certain way, and we are expanding it with more cognitive architecture of how to store the persona, right? The person's, essentially, this is a very interesting problem, because compared to previous one, which says which movies you will like, this is saying what you won't know. So that was a positive prediction, what your behavior might be. And this is a negative prediction, what you may not know, what your behavior might not have been, right? So the two are very different, fundamentally different. And there is a theoretical reason to believe that this is a harder problem, to predict what a person doesn't know. And personalization is even more important in this kind of cases. Like culture as a prior helps less here. So this tool exists, and I will tell you some experiments and some results that we had from this tool to see, to what extent, again, personalization can work and how good are LLMs. So to do the study, we chose books from 3 countries, India, USA, and Ethiopia. And we chose users also from 3 countries, India, USA, and Mexico. And we gave these users to read reviews of these books from Goodreads. Goodreads is a website where people post good reviews. So they read reviews and they identified what things they did not understood or found it hard to understood. Now, the first thing, I think, I don't have it here, but if I remember correctly, we had around 50 books total annotated by 50 users, something of that sort. I mean, that's roughly the scale of the experiment. Now, what was interesting, first of all, let me tell you the most obvious thing, more like a baseline check, that should Indians know more about Indian books, right? We expect Indians know more about Indian books and find less things difficult. And USA people will know more about USA books and all. And this is indeed happening. So these graphs show what was difficult. Blue means nothing was difficult, and the other 2 colors mean something was difficult, and we further classify them as whether it is because of a cultural reason or non-cultural. This was a annotation done later through human in the loop LLM. And non-cultural example could be a complex word, right? A very complex English word. And cultural reason are, of course, you understand, like references to things like golden arches and all these things, which are maybe people from that geography not really familiar with. So this does happen. So if you see Indians, they find, kind of, and if you see book origin, which is from India, they find 21%, 34% things are difficult here. Whereas the other thing, let's say, if you look at here, so Indians, Mexicans in Indian books find 38% things difficult, and USA in Indian books find 41% difficult. So in short, Indians find Indian books least difficult. And same, you can see the pattern is there also true for USA. So this is the baseline check. The other thing we want to say is for all reviews, 80% of the reviews, there was something which was culturally specific, which somebody found it difficult, which also gives, establishes the need for building this kind of a tool. So there are cultural things which people usually don't understand. Okay. Now, what is the inter-annotator agreement between people? I will just look at, let's just look at this. These are just details of breaking down into inter-annotator agreement into various other specific things. But overall, if you look at inter-annotator agreement, so typically Mexicans agree more with Mexicans annotations, Indians agree more with Indians, but between countries, the agreement is poorer. Somehow USA people don't agree with the USA people more. And this might be because USA is a very heterogeneous country, right? Like people from all over the world go and settle there. And we did not do a thorough control of the exact cultural history of the people. We just looked at where they were at the moment and did they identify as a person from USA. So that might be the reason. Now, if you look at culture-specific items, these numbers grow up, go up. So Indians typically agree with Indians on culture-specific items more commonly, and Mexicans, like what they find difficult, right? They agree more commonly. So again, another reason why that this data set makes sense. It's just like what we would expect. Now, what happens with machines, LLMs? Now, this is what is interesting. So let me tell you the experiment a little bit. So human data we have already, right? And we can ask LLMs to sort of also annotate what a Indian of a certain age group, etc., will not understand in this review. And that becomes my simulated data from LLM. And we used a lot of LLMs, Mixtral, Mistral, Llama, etc. And now we are doing a pairwise inter-annotator agreement. Like, did Gemma's annotations agree with GPT-4o and how much it agreed with human and so. Now, what is interesting is, and this is divided by the population country from which the population was drawn. So India, Mexico, and USA. And what is interesting is first look at the last row. So humans typically agree with humans to a certain extent, like 0.1415 and 11. Like this is like the previous result that I was talking of. Like there is an agreement between humans, but machines, LLMs, don't agree with humans at all. These are close to zero, sometimes even minus, in the opposite direction. So there is no signal here. However, machines seem to agree with each other quite a bit. See, all cases, machines seem to agree with each other quite a bit, LLMs, right? And if you see like GPT-4o agrees with Gemma quite a lot, 0.56 and so on. What is happening? So what does it tell us? So it tells us, so this is the observation, models agree more between themselves than humans do. It's even more than what humans agree between them, right? So that tells you that humans have much more variation between them in any group than models have. And second is, models agree far less with humans. And this is the surprising thing. So I think the reason for this is what models are trying to learn is stereotypical behavior from cultures, right? They are trying to learn the stereotypical behaviors. And yes, all users belonging to a culture exhibit some of this prototypical or stereotypical behavior, but no user exhibits all the prototypical behavior of the culture. We are all unique in ways, even though, let's say I'm an Indian, but there are parts of my behavior which is un-Indian-like. And this is true for all of us. And this is what models don't get. So when they hear Indian, they will throw out a prototypical behavior. And there is very little variation. So all models do the same. So models agree with models. But humans are not like that. And therefore, models can't actually mimic humans. Now, this has very strong repercussions, right? One strong repercussion is LLM as a simulator of culture is very, very dangerous. So a lot of studies try to use LLMs as a simulations for cultural studies. But if LLMs don't have the diversity that humans show in real world, then LLMs are very bad, representations of culture. Second hard point, important lesson from here is if you use LLMs to distill, then you are sort of building in the bias or the stereotypical behavior more and more and losing the long tail and richness of the behavior that humans display. So this is another danger that we have if we distill. Of course, I'm mindful of the point some of you might be thinking that why even we want to model culture, we want to only try to do utility-centric thing. And if there's a use case, we only want to solve that use case. And I totally agree there. But most of the LLMs don't have a use case, right? I mean, we don't build them as a use case centric model. We build them as generic model. We claim them to be AGI. And this is the point that they are not really good models yet of the diversity of human behavior. So now, wrapping it all up, then what's the philosophical repercussions and some of the interesting open questions of this Turing test 2.0 based on the study that we saw so far, the two case studies, but even otherwise? I will start, before getting into philosophical questions, start with a very practical example of how being able to simulate or solve an individual or solve Turing test 2.0 can be profoundly useful. And this example comes from the domain of mental health. So there are lots of mental health conditions or ailments which can be solved reasonably well if there is the right kind of intervention. But the problem is mental health is so broad. Like, and let me give a concrete example. Let's say autism. So recently, Donald Trump, there was a report that apparently in the US, every third child is on the autism spectrum, right? Every third child. So it's shooting up to an amazing extent. In India, the ratio, it's like every 10th person. But it might be also underreported, underdiagnosed, and so on. But the thing is, the spectrum itself is pretty wide. Not all autism people with autism are same, and that's why it's called spectrum. It's huge variation there, huge variation. Now imagine we could do this. So here is a child. I collect the background and history, and also I collect some conversations, behavioral signals, and other things about this child, and pass it to an LLM. The LLM does some sort of fine-tuning, RLHF, whatever you can imagine, and creates a digital twin, which is the user model of this particular person. And then I have a whole bunch of potential interventions, right? So there is occupational therapy. There is, I don't even know all the names, but imagine there are so many, like a almost potentially infinite set of interventions, because there is a finite set, but their combinations are also possible, right? So various combinations and goes to almost a huge set. And I could actually simulate this intervention on the digital twin and see what's happening. And based on that, based on the outcome, I can suggest a optimal intervention, which then the therapist can take. And I'm not saying the AI should do the intervention. A human therapist can do the intervention, but it is actually helping the human therapist to come up with the optimal intervention through the digital twin. Now, why this is so important, right? Why the therapist can't think of these interventions? Because the space is so diverse that a therapist would not have experience of treating so many patients. And another thing is the number of therapists are much less than the number of incidence cases. So this could be an extremely useful case. And recently I was in a Dutch tool seminar in Germany. Dutch tool is a place where you do like very small group intensive discussion. And this particular Dutch tool was in NLP for mental health. And there I presented this, and other people like in Stanford and UW, they are also working on these simulations of patients. So it's a hot area of research. It's not something like very futuristic. It's happening at the moment. So this is a huge potential. Some people are also trying, in fact, instead of this loop, some people are asking the therapist to play with the user model and use this as a training for the therapist. That's also another way of thinking about it. So all these possibilities are there. Now, you might ask, if that is the case, then what is the ethics of it, right? What are the privacy concerns here? What about, so the benefits are fine. I already gave examples of treatment and therapy. There is simulacra, personalization has all sorts of other like standard benefits. But what about privacy? What about manipulation? If somebody knows your behavior so well, like marketing agencies, they can manipulate, right? You. What about deepfakes? So these are all very valid questions. We should think about it. I don't want to get into too much of detail here in this talk, unless there is a question, except for one thing I will mention. If you're building a specific use case like this, you don't need to build a digital twin in the sense that you don't need to replicate every behavior of the person, right? You don't need to replicate, for instance, which songs the person likes. It may not be relevant. You only need to replicate the relevant behavior, and the user model should be good enough that the response to the intervention mimics the response to the intervention by the actual person. So that is the level at which you want the, symmetry. Beyond that, you don't care exactly how things are being said by the person, what language and all these things. You probably don't care less. But it is more like our aim here is to get the correct intervention. So the intervention and response to different intervention, that part should be modeled accurately. Now, it's a very hard problem. So we are working with psychologists. So this is a problem I just started working on in the space of autism. And we are talking to psychologists, and they also have very little understanding and what behavior needs to be replicated and what doesn't need to be. And all these things are very open question. In fact, we don't understand mental health very well as a science. I didn't know all these things. It looks like psychologists knew all of it. Turns out they don't know anything. I mean, they know very little. So most of the time, the therapies or interventions work only 20% of the time. So you can imagine, like, it's a very low, hit ratio. So all these concerns are there. And I will end up with two open questions. One, one interesting question about behavior, and it goes back to this previous question of which part of behavior I model, is about what behaviors can be transferred between domains. So if I know your movie choices, can I predict your food choices? And it so turns out that anthropologists have looked into these questions, and there are good correlations and predictors in some cases, but there are not many very foolproof, theories around it. So there has been studies, some are positive, some are agnostic, open, some are not very clear. So to me, that's a very interesting question. Like, if I know behavior in certain domain, can I predict behavior in some other domain? And this is equivalent of transfer learning, right? Like, if I can do very well in one language, can I transfer the knowledge for another language? And we know that cross-lingual transfer happens. But does cross-domain transfer of culture or cross-cultural transfer of behavior, those things happen or not? We don't know. The second is, I already mentioned, limits of prediction. So human behavior is a very complex system. It's actually a second order complex system, which means by predicting the behavior, you will actually change the behavior. So since it's a second order complex system, predicting till the very end is definitely not possible. But where is the limit? And most importantly, if I'm trying to solve this problem, how do I know that I have hit the limit, right? Like, I know the inversion point from my graphs, but is it the real limit or limit of my data or limit of my model? So that's also another very interesting, broad scientific as well as philosophical question. With that, let me end, and I will be more than happy to take questions. And this is the group, a lot of people have contributed to it. And, if you are interested in knowing more, check the website, check the papers, but also, please feel free to reach out to me. We have open positions at multiple levels, like PhDs, masters, and also research engineers. Yeah, okay. So let me see if there are any questions.
Yeah, thanks a lot. Thanks a lot. Are there questions from the class offline?
No questions.
No questions?
Okay, Monojit, then we'll finish the class.
Okay.
Really appreciate your time.
Thank you. Thank you.
Yeah.
It was a pleasure.
Thank-
And again, I hope I was there. Yeah, in person.
Thank you.
Thank you. Bye-bye.
Bye.